Hello. So let's start the class. As I've announced in last class on Wednesday that Friday class will be there will be no Friday in-person class, and I'll be doing this video lecture. So that's what I'm doing now. The goal here is to do another problem from chapter 14. We started with a problem in last class. Let me see if I can show it to you quickly, doing an overview. Okay, in last class problem, we introduced a new equation called principle of work and energy. The equation that you're seeing here, which has T1 is the kinetic energy at state 1, T2 is the kinetic energy at state 2, and summation of forces, summation of energy from state 1 to 2, like all other forces related energy. As an example, in last class, we had the spring, so there is this spring force and the spring energy. We had this external load F equal to 100 Newton, so we had this external load and energy or work related with this 100 Newton external force. Basically, the way you can find it, as I've shown before, you just have to multiply the distance traveled with the external force 100, and for a spring we use the half kx square. The x is the displacement, and it would be written by s2 minus s1. Those are the position, and we use all those things, and we solve for the final location s. That was the problem, and that problem was a little challenging because that was an inclined surface. Okay, and today's problem that we are planning to do is this one, where we have a I don't know if you ever seen this thing. I mean, even in Watertown Mall, they have one of the setup where marble is kind of circulating through different channels. This one kind of similar to what I was just trying to explain over there. Here we have this curve shaped AB tube where a marble is flowing through from A to B, and then once it passes through B, it's on air, free fall, and it has a projectile, and finally it just fall into C, location C. So the question gives you some value like the marble mass. I'm sorry, it is happening. Okay, the mass of the marble, which is 5 gram, and the question gives you the location where all these things are happening. As an example, here the location A is 3 meter above, or the altitude is 3 meter from location C. Okay, location B and C, the altitude is 2 meters, so that's another thing is given. So those are all givens. So what we're trying to find, we're trying to find the position of the can, this can we are talking. Okay, basically we got to find the value of the r. Okay, so the marble, when it comes, it won't fall into out of basket. It needs to be on the basket or the can. All right, so to find that, obviously it says neglect the size of the can and everything. To find that, we got to obviously use these work energy equations, right? So let me do a quick sketch. So we do have the marble when it is flowing through, it has this free fall, weight W has mg, right? M is the 5 gram. So if you wanna start with the givens, right? So three things are given. First of all, the mass of the marble is given as like 5 gram, right? I can say 5 gram this way as well, and then the altitude difference, which is I don't know, maybe you can say like y a to b, sorry, a to c. That one is y a to c, or ac. That we're gonna say as well. So this one will be y bc, right? So you have those two dimensions given as well. So y ac, which is 3 meter, y bc, which is 2 meter. So these are the givens. Okay, and you are trying to find, let me do it here, find the value of r. Okay, so let me talk about the strategy, how we're going to solve it. Okay, so first thing, you can use this equation, the equation that I started with the class, right? Work and energy equation, here. Okay, on this work and energy equation, you have this change of kinetic energy at position 1 plus the work and energy involved from position 1 to 2 is summation of change of potential energy at state 2. Now this 1 and 2, that could be referred in this particular case I was trying to explain from A to B. Okay, if you're going to consider that is going from A to B, then obviously this would be from A to B and this would be B, right? There is little overriding. I can rewrite that whole thing here. Okay, so A to B and then B. Okay, so what you can find from there? First of all, they gave you this clue here. At location A, the marble is at rest. So what does it mean? It means the velocity at location A is 0. Okay. Now, obviously, when the marble is flowing through the curved tube at position B, it does have a velocity, right? So there is a VV velocity, right? And there is a velocity as well when it's dropped at basket or can C. So there is a velocity at BC. Okay, let's now focus on this AB tube only. So the equation that I just showed it to you, what that equation can give it to you? The equation can give it to you the value of the velocity at location B. Why? Because if the ball start from 0 at location 1, right? So then obviously this will gonna go away. We'll only have this KEB. Now you know this KEB is half of MBV square, right? So where the M is known is the weight of the marble, right? And the UAB, that should be written as the weight or the force, right? Force of the marble. You see on the sketch I did write what is W, weight W, and then the distance that it can travel. Now the distance that it can travel, you can find it this way. So like, so sorry, just 1 second. Yep. So the distance you can find it from YAC minus YBC. Okay. All right. So now when you're going to use these equations and everything, you should be able to find the value of the VV with no problem. Okay. So that's the BV or the velocity at location B. Okay. And what you're going to do with this velocity? Okay. Now take a look here. To find the value of R, so to find the value of the R, so this R I'm talking, to find the value of the R, you have to use this equation where you have this initial location x0, say like this is your x0 value, right? Say this is x. And here, this is your final location, right? And that's your R, right? So that would be considered as R or XC in this case. So that is R. So XC, and this x0 could be explained as XB. So basically, you can use this equation where you need to use this BV and then T. And how I'm doing it, because this block here, this marble here, when it travel, it has an initial velocity in x direction. Okay, is BV. That's the constant initial velocity, right? And that's why I can use this equation. Now, once I have this value, the R value, then I'm done. But the problem here that you see several of the parameters that I don't know. First of all, I do know this, right? This is at 0, like if you can consider that. And I do know this, the VV from the thing that I explained before, right? By solving that equation. So this is known as well. So this T is unknown. Now here's the thing, the challenge. So how to find the value of the T? So when the marble as its location B and it acts like a projectile and falling into the can C, you can use this projectile equation in y direction. Remember the y in this case, it should be final location y, that means YC, and then YB, right, plus Vy0, okay, multiplied time t plus half of G time t square, right? So from this equation, you should be able to find the value of the time t. Now, how? It's very straightforward. When the ball is at location C, there is no vertical distance, so this would be 0. When the ball starts from position B, it's just going on this tangential x direction velocity. There is no y direction velocity. So this would be 0. So that would be 0 as well. So you can solve this equation and find the value of the t. Okay, everyone got it? All right, now let's start with the actual solution. Okay, so let's do it here, I guess. So here, solution. So those are whatever I explained so far are just a note or strategy. Okay. So you want to obviously start with I'll also find the value of the BC. Okay, the final velocity. Okay. But before I do any of this thing, let me start with this equation. So you're going to use the work and energy equation to solve. So we're going to solve two things. First, the velocity at C and the velocity at B. Okay, let's go one by one. So we have this equation. We know change of kinetic energy at location 1, change of energies from 1 to 2, and change of kinetic energy at location 2. Now I'm saying like location 1 and 2. When I'm saying location 1 and 2, it can be considered literally anything like A to B or B to C. So I'm going to go with A to B in this case. So I have this equation for kinetic energy, and then I can say this is A to C. Okay. Let's deal with A to C to find the value of the BC first. Okay, and then we're going to find the BB. So A to C, and then I have this equation half of M BC square. All right. So here, obviously, we know initially the velocity is 0, right? And then I was explaining that what are the energies involved. So this sketch can help you to find that the weight W acting downward, right? So that's why you have a negative here, and then you can put this distance, right? Distance multiplied force is the work. You know that, right? So the distance would be YC minus YA. Okay, and then you have half of M BC square, right? Now you know YC minus YA is basically this 3 meter that I did talk about it before. So 3 meter, right? So I'm gonna write minus mg, then 3 meter, right, multiplied half of mbc square. This m and m will going to cancel out. So if you're going to try to find the value of the bc, so then you got to rearrange some of the things. So 3, okay, and then you're going to plug the value. Okay, this could be meter square per second square, the whole thing. So 2 multiplied 9.81 multiplied 3, and you can do the square root to find the BC, and the unit would be meter per second, right? And then you do the math, you're going to come up with the value of BC as like 7.67 meter per second, right? All right, so then as I was just talking about the strategy, right? Before finding the value of the R, so now you're trying to find the second part of the problem. So find R. You know what is R again. Okay, so that's the distance between location B to C in X direction. Okay, so then you'll be using the same equation like the kinetic energy at location A plus summation of U A to B, this time A to B. Okay, and summation of kinetic energy at B. Now you know it's always 0, right? A to B, and then in this case just similarly you're gonna do like YB minus YA. By the way, this is 3 minus 2, that distance I'm talking. Half of MBB square, right? I explained it already, so I won't be doing the same thing. There is a negative because the gravity is acting downward. And then this BB can be rewritten just the way I was explaining before, this 2G YB minus YA. okay? And you know this distance of YB minus YA is 3 minus 2. Now, in case if you're wondering, take a look on the sketch. So YAC is 3 and this YBC is 2. So that's what we're doing. So that's 3 minus 2 square root. You're going to keep it as it is, right? And then this thing is PV. The unit needs to be meter per second. And then you're going to plug all the values, which would be 9.81 multiplied 1 meter per second, the square root. And then you'll have a value of 4.43 meter per second. That's your PV. All right. And then I already explained all the strategy, right? To find the R, you gotta use this equation R equal x0 b t, but bbt. But before you do that, let's write this equation, y direction equation. So which would be yc, right, equal yb plus by0 multiplied t, okay, plus half of gt square. Now I did explain it already, so this will be 0, and then you have this yb, actually you can write it ybc as well, right? Okay, so ybc is 2, we know that from the sketch, and this is 0 here. This is half of 9.81 meter per second square multiplied t square, right? So you'll already arrange stuff and to find the value of the t square. So you'll have t square multiplied 4 point, so this is 9.81 divided by 2, right? And then this whole thing should be equal to, then by the way, this 9.81 is negative, so there's a negative sign, equal minus 2 meter, right? So this m could be confusing as like, is it a mass? No, this is a meter, so the m was the unit. Okay, so let's just not write the unit for now, and then start to solve this. So the t square will going to become 4 divided by 9.81, right? 9.81. Now obviously this would be second square, the final unit you can write here, as long as you keep up with the base unit. And then this t should be square root of obviously 4 divided by 9.81 second, which would be 0.64 second, right? And that's the final part that we are solving now, which is the location of r, or the value of the r value. Again, if you forgot, the r is the distance from b to c. So to find that one, we're going to use simply the equation r equal x0 plus bb in this case, okay, multiplied t. Now I did explain this thing before, I'm just rewriting that just in case if you're wondering. Now x0 is 0, I did explain it before, so the r should be, you have the value of vb, which is 4.43 meter per second, multiplied by the t is, this is by the way second, right, not 5, so 0.64 second. This second we're going to cancel out, and you'll have a value of final answer, which is 2.8 meter. Okay, so that's it from me today. Now let me do a quick recap. We actually use in this problem the work and energy equation twice to find the velocity of VV and VC. All right, and we use the projectile equation one time, like the y direction equation, to find the time t, and the x direction is equation to find the value of the r. That's it from me today. Okay, you have a wonderful day. I'll see you on Monday.